Crunch, cream, and pure perfection define the world's most beloved cookies. From the iconic twist of an Oreo to the caramelized crunch of Biscoff and the delicate layers of a Milano, each one follows a precise and mesmerizing process of baking mastery. Today, we uncover how these famous cookies are mixed, molded, and baked to perfection inside the factories that turn simple dough into global legends. Each day, over 40 billion Oreo cookies are produced, enough to give every person on Earth more than 5 cookies per year. And that global flood of cream-filled chocolate wafers starts with a process so precise, so standardized, it runs almost like a living organism. Dozens of machines moving in perfect sync, churning out America's favorite cookie with millisecond timing. It begins with 2 simple-looking ingredients, cocoa powder and sugar. But these aren't your grocery store versions. The cocoa is Dutched, alkalized to reduce acidity and deepen its color to that signature Oreo black. It arrives in fine, dark clouds, poured from towering silos into mixers where it meets finely milled wheat flour, sugar, leavening agents, and a custom fat blend designed to give the cookie just enough snap without crumbling. Everything is sifted, weighed, and blended by machine to microscopic consistency. Mixing happens in industrial stainless steel vessels large enough to bathe in. The goal is a fine, uniform dough, and time matters. Too long and it gets tough. Too short and it won't roll cleanly. Once ready, the chocolatey mass is extruded onto a conveyor and shaped into flat sheets that glide through a series of heavy steel rollers. These roll out the dough to exactly the right thickness, about the width of 3 stacked playing cards. But here's the first real moment of magic: embossing. Every Oreo gets stamped with its iconic pattern: 12 flowers, 12 dots, and a central logo, pressed by engraved rollers that move in time with the conveyor. These molds aren't just decorative. They create surface texture that helps the cookie bake evenly and gives that perfect crisp when bitten. The alignment is so precise that even a slight misprint sends cookies off to a reject bin, where they'll be ground and recycled back into the dough. Once cut and stamped, the cookie rounds head into the oven, an industrial tunnel more than 100 feet long, with zones of carefully controlled heat and airflow. The aroma here is intense, a rich mix of roasted cocoa and warm sugar that hangs in the air like fog. Cookies bake for a few minutes, firming up and darkening as moisture escapes. They move continuously, baking on the move, emerging on the other end dry, crisp, and still piping hot. Next comes cooling, which might seem simple, but it's a whole engineered step in itself. The cookies must cool from nearly 200 degrees Fahrenheit down to room temperature without absorbing ambient moisture or warping in shape. They travel through long cooling conveyors, multi-tiered steel spirals that snake upwards like parking garages. Air is filtered, humidity controlled. No fans blowing in contaminants. The cookies are too fragile to stack or crowd, so they ride in single layers, perfectly spaced. Now comes the creamy middle, but it's not quite what most people think. Oreo cream isn't buttercream or frosting. It's a specially formulated shortening-based filling made from a blend of oils, sugar, and flavorings, whipped at high speed until fluffy but firm. This mixture is pumped into hoppers above the cookie lines, where it's deposited with high-speed nozzles. Each nozzle fires a perfect dollop, precisely measured, exactly centered, onto every other cookie as it glides past on the line. And then, the sandwich. Top and bottom cookies are pressed together by a gentle machine called the twister. It's not spinning, it's calibrated pressure, just enough to seal the cream without cracking the cookie. Some factories even chill the cream slightly, so it sets faster and holds the sandwich firm. But before any Oreo can be packed, there's one more checkpoint: visual inspection. Modern Oreo lines use vision systems, fast, high-res cameras that scan each cookie for imperfections. Is the cream off-center? Is one cookie misaligned? Does the embossing look muddy? The system flags flaws in milliseconds and a puff of air knocks flawed cookies off the belt and into a discard bin. Perfect sandwiches continue onward to packaging, which is its own ballet of motion. First, the cookies are grouped into stacks, typically 3, 6, or 12 per pack. Robotic arms, guided by sensors, nudge them into plastic trays at blinding speed. These trays are pre-formed and loaded automatically, gliding into position just as the cookies arrive. Next, flow wrappers roll out the familiar blue plastic film, coated to resist moisture and air. A measured length wraps around the tray, sealed by heated jaws that crimp the plastic closed on both ends. The wrapper must be tight enough to hold shape, but loose enough not to crush the cookies. A tiny notch is added to help with opening. Yes, even that's automated. Sealed packs are printed with batch codes and best by dates using inkjet systems that can mark hundreds of units per minute. They move onto the final packing stage, where robotic arms, nicknamed pick and place, lift dozens of wrapped packs into cardboard boxes. Each case is weighed to ensure no underfilled packs slip through. If a box feels light, it's kicked off the line for inspection. Full cases head to palletizers, towering machines that stack boxes with geometric precision. These machines use suction, vision, and pressure sensors to build stable pallets ready for shipping. Pallets are wrapped in plastic film, barcoded, and logged into a warehouse management system. Then it's off to the loading dock, where trucks ferry Oreos to supermarkets, gas stations, vending machine suppliers, and even cruise ships. What's wild is how little human hands touch any of it. Operators oversee the lines, check monitors, and handle maintenance, but the cookies themselves move from flour to finished pack without direct contact. That's partly for speed, but mostly for hygiene. Food-grade factories are designed like clean rooms. Employees wear full-body suits, hairnets, and shoe covers. Airlocks separate production zones. Every surface is washable, and equipment is designed to come apart quickly for cleaning. Some facilities even run conveyor belts under UV light to kill microbes between shifts. And the entire system is designed for consistency, whether an Oreo is made in New Jersey, Mexico City, or Indonesia. The size, taste, crunch, and even the way the cream peels off have to match. That requires astonishing control. Even the water used in dough mixing is filtered and temperature regulated to ensure it won't throw off the texture. Behind the scenes, data pours in from every part of the line. Temperatures, belt speeds, fill weights, reject rates. Algorithms fine-tune the process in real time. If humidity creeps up on a rainy day, the system may adjust bake time by fractions of a second. If embossing starts to fade, the rollers may be cleaned or swapped out without stopping the line. There's also testing. Dozens of cookies per shift are pulled and sent to quality control labs. Here, they're broken, crumbled, measured, and sometimes even dissected. The cream layer gets scanned with a laser to check thickness. The cookie's texture is analyzed using a machine that mimics biting force. And of course, taste tests, conducted under strict protocols, so sensory panels can detect the tiniest shifts in flavor. And those variations matter. Oreo has spun off into hundreds of flavors and formats over the years, from green tea in Asia to birthday cake in the US to peanut butter, carrot cake, lemon, and more. Each variant has its own custom process, sometimes a different cream formula, sometimes a different bake time, sometimes entirely new tooling for the embossers. The engineering behind a limited edition Oreo can take months, just for a product that might only be on shelves for a few weeks. Some plants even produce double-stuffed Oreos on the same line as regular ones. To switch, they simply recalibrate the cream dispensers to add more filling, roughly 1.86 times as much. Not quite double, but enough to earn the name. For mega stuff or thins, different mold cavities are swapped in, and the machines reset accordingly. Everything's modular, built for speed and adaptability. And still, the most impressive part may be just how unbroken the chain is. A single Oreo pack might take under an hour to make from start to finish, and yet it's the result of more than a century of engineering refinement. From its origins in a New York bakery in 1912 to the massive factories today, the Oreo has become one of the most duplicated, studied, and optimized cookies on the planet. Every year, more than 6 billion Biscoff cookies are baked in a single factory in Lembecky, Belgium. That's about 17 million per day, or nearly 200 every second. And while they may look like simple caramelized biscuits, the process behind that thin, crispy snap and warm spiced flavor is anything but basic. It starts with a dough unlike most commercial cookies. There's no chocolate, no cream filling, no artificial glaze. The signature Biscoff taste comes from a blend of brown sugar, wheat flour, a precise mix of spices, mostly cinnamon, and vegetable oils. The brown sugar is critical. It caramelizes during baking, giving Biscoff its golden color and deep toffee-like flavor. In the factory, massive silos hold fine wheat flour, while the sugar, coarser and darker than typical white sugar, is pumped in from nearby storage tanks. Liquid sugar blends, often made from beet or cane molasses, are also added to intensify the caramel notes. This mixture is loaded into huge industrial mixers, each the size of a small car, where the dry and wet ingredients combine into a soft, sticky dough. Unlike cookie doughs that include eggs or dairy, Biscoff is entirely plant-based. That's part of what gives it such a long shelf life, and what allows it to crisp up so uniformly. The mixed dough is portioned and conveyed into giant rolling systems. These rollers flatten the dough to just a few millimeters thick. From above, steel die cutters stamp out the iconic rectangular cookie shapes, complete with the Biscoff name embossed into each surface. The cutouts are tight and efficient. Almost no dough is wasted. What's left between the cut cookies is immediately scraped up and recycled into the next batch of dough, which gets re-rolled and stamped all over again. It's a loop that continues with incredible efficiency, ensuring minimal waste and perfect consistency across billions of units. Once shaped, the cookies ride onto a baking belt, a high-speed mesh conveyor that carries them through a tunnel oven over 200 feet long. This oven is divided into zones, each with specific temperatures and airflow patterns. The cookies begin to bake almost instantly. You can smell the transformation as it happens: warm cinnamon, caramelized sugar, and toasted flour building layer by layer. In the early oven zones, moisture evaporates rapidly, and the sugar starts to caramelize. By the middle of the oven, the cookies take on their golden brown hue. Near the end, airflow is carefully controlled to set the cookie structure and ensure a crisp finish. If the airflow is too strong or uneven, the thin cookies can warp, crack, or brown inconsistently. Getting the bake just right is a blend of engineering and chemistry. Seconds too long and they become brittle. Too short and they're soft. Fresh out of the oven, Biscoff cookies are extremely delicate. They're hot, fragrant, and prone to snapping if touched too soon. So they move through a cooling tunnel, a winding conveyor belt that loops through a climate-controlled chamber. The cookies cool slowly, with filtered dry air preventing condensation. Cooling too fast would crack them. Cooling too slow might cause them to absorb moisture and lose their signature crispness. Once they reach room temperature, a visual inspection system checks for flaws. High-speed cameras scan every cookie for breaks, uneven coloring, or misaligned embossing. Imperfect cookies are flicked off the line with tiny jets of air, no humans required. Perfect cookies continue to packaging. For the classic single-serving packs, often found on airline trays or coffee shop saucers, cookies are grouped and aligned in neat rows. Robotic arms gently push them into narrow slots in packaging lines. Thin plastic film is pulled from enormous spools, cut and heat sealed around each group of cookies. These machines run at blinding speeds. often packing hundreds of units per minute. For retail boxes, the process scales up. Cookies are stacked, wrapped, and boxed with exact counts. No broken pieces allowed. Sensors weigh each package to make sure none are underfilled. Any off-weight boxes are kicked off the belt automatically. Each pack gets a date code and lot number printed with food-safe ink, tracked digitally so the company knows exactly when and where every cookie was made. What makes Biscoff truly fascinating from an engineering perspective is how streamlined the entire process is. The entire global output, billions of cookies, is made in just a handful of production lines in one place. Everything is optimized for speed, precision, and minimal manual intervention. Hygiene is also a key priority. Even though the ingredients are simple and baked at high temperatures, the factory is managed like a clean lab. Workers wear full sanitary gear. Airflow in the plant is controlled to prevent dust contamination. Equipment is designed for easy disassembly and cleaning between production shifts. Stainless steel surfaces, air filtration, and dry cleaning systems, since moisture is the enemy of crisp cookies, are all part of the daily routine. Even the spices are handled carefully. The cinnamon that defines Biscoff's aroma is stored in sealed containers and measured precisely. Too much and it overpowers the caramel notes. Too little and the flavor becomes flat. Every batch of dough is taste tested in micro batches before scaling up to full production. And then there's the spread. Biscoff cookie butter is made by grinding finished cookies into a fine, sandy powder and blending it with oils and stabilizers to form a creamy, spreadable paste. The production line for the spread is entirely separate from the cookie line, but it starts in the same place, with baked Biscoff biscuits. They're deliberately overbaked to reduce moisture even further, ground in large industrial mills and blended with oils until smooth. The paste is vacuum sealed in jars on high-speed lines, then labeled and boxed just like the cookies. Every part of the process is a study in precision. The cookie's thinness means the margins for error are razor slim. Even a small change in humidity, ingredient temperature, or roller calibration can throw off the final product. So engineers monitor every step, from flour intake to final sealing, using data feeds from hundreds of sensors across the line. Algorithms track trends, make predictions, and automatically adjust the machinery to stay within spec. And despite the scale, the final product still feels handmade in its simplicity. No artificial glazes, no multicolor branding, no flashy inclusions, just a thin, crisp, cinnamon-kissed biscuit designed to pair perfectly with a cup of coffee. The entire Biscoff factory operates almost like a symphony. Machines mixing, stamping, baking, cooling, inspecting, and wrapping in an unbroken rhythm. The smell of caramelized sugar hangs in the air. Everything hums. And every second, dozens more golden cookies roll off the end of the line, uniform, unbroken, and ready for another flight, cafe, or cookie jar. Milano cookies were never meant to exist. They were born as a fix. In the 1950s, Pepperidge Farm's original Naples cookies, two delicate oval butter cookies with a dollop of chocolate, kept melting together during shipping to warmer climates. So the solution? Add a second cookie on top to protect the filling. That happy accident created the now iconic sandwich. Crisp, airy cookies wrapped around a smooth ribbon of dark chocolate. Today, every Milano cookie is still made using a surprisingly intricate and carefully controlled process, engineered to keep the experience light, elegant, and unmistakably crisp. Production begins with a rich, butter-based dough that's deceptively simple. The ingredients include real butter, sugar, cake flour, eggs, and a bit of salt. But the texture is everything, and that comes from how it's handled. The butter must be at the right temperature to cream properly, forming a smooth, aerated base. Too cold, and it doesn't mix evenly. Too warm, and it starts melting, ruining the final structure. Giant planetary mixers, Imagine industrial-sized kitchen stand mixers beat the butter and sugar until pale and fluffy. Then the eggs go in slowly, followed by flour, sifted in under vacuum to prevent clumping. This dough is extremely soft, closer to a thick batter than a traditional cookie dough, and that's intentional. Milano cookies aren't rolled or cut, they're piped. Once mixed, the dough flows into pressurized piping machines equipped with dual nozzles. These nozzles deposit neat ovals of batter, just the right size and spacing, onto long, non-stick baking belts. Each cookie is formed by a controlled squirt of dough that drops, spreads slightly, and sets. No molds, no hands, just pressure and programming. The unbaked cookies glide into tunnel ovens that stretch the length of a semi-truck trailer. Inside, heat builds gradually. Early on, steam from the butter lifts the dough, giving it that puffed, almost sponge-like texture. As the cookies bake, the sugars caramelize slightly, giving them a light golden color and delicate crispness. The timing has to be exact. Just a few seconds too long, and they darken or turn brittle. Too short, and they stay soft or collapse when cooled. As the cookies emerge, the smell is unmistakable. Warm butter, vanilla, and just the faintest hint of browning sugar. At this stage, they're incredibly fragile. A puff of air could break them, so they're gently transferred to cooling conveyors, spaced to prevent contact. These conveyors snake upward through multi-tiered cooling racks, where ambient air, filtered, chilled, and dehumidified, brings the cookies down to a stable temperature. Meanwhile, the chocolate filling is prepared separately in temperature-controlled vats. Milano chocolate isn't gooey like ganache or sticky like frosting. It's a firm, snap-able layer made from a proprietary blend of dark chocolate and cocoa butter. The chocolate is tempered, which means it's heated, cooled, and reheated through a precise curve to form stable crystals. This gives it a glossy finish and a satisfying snap when bitten into, without melting too quickly on fingers. The tempered chocolate is loaded into precision depositors, metal hoppers fitted with nozzles that release the chocolate in exact amounts. Half of the cooled cookies are flipped upside down and roll beneath these nozzles. A narrow stripe of chocolate is deposited in the center of each one, just thick enough to bind, but thin enough to leave room for the cookie's crisp texture to dominate. It never reaches the edges. That's by design. The clean look and controlled chocolate distribution keep the cookie balanced. Never too rich, never too dry. From there, the second cookie is gently pressed on top by a calibrated roller that applies just enough pressure to seal the sandwich without cracking the shells. These sandwiching machines are incredibly delicate. Each Milano cookie is different by fractions of a millimeter, so sensors adjust in real time to apply slightly more or less pressure depending on alignment. It's like assembling a luxury watch, but edible. After sandwiching, the cookies must rest. This resting period allows the chocolate to set fully and bond the cookies together. If they were packed too soon, the warm filling could cause moisture migration, softening the bottom cookie and throwing off that signature crisp texture. So the cookies ride on another slow-moving belt through a final tempering zone where the air is kept cool and dry. By the time they reach packaging, the sandwiches are firm, light, and locked into their signature structure. Packaging Milano cookies is a quieter, more deliberate process compared to high-volume snacks like Oreos or Biscoff. Each cookie is placed into a custom-molded plastic tray that keeps it from shifting or rubbing against its neighbors. These trays are then loaded into the iconic white bags, triple layered to block light, moisture, and oxygen. Even the bag's fold and seal top is part of the design. It's meant to recreate the feel of a bakery bag, reinforcing the idea that this isn't just a snack, it's a treat. And unlike many mass-produced cookies, Milanos are made in relatively small batches. The focus is on control and consistency, not just speed. Production lines are slower, and each line is dedicated to a specific flavor at any given time, whether it's classic dark chocolate, mint, orange, or seasonal variations like raspberry or pumpkin spice. Switching flavors isn't just a matter of swapping ingredients. The machines are cleaned, recalibrated, and flavor tested before a new batch begins. Any leftover dough or chocolate from a previous run is discarded to avoid cross-contamination. There's a surprising amount of sensory testing involved as well. Milanos are thin enough that any change in dough aeration, bake time, or chocolate viscosity can throw off the texture. In on-site labs, quality control technicians regularly test cookies from each batch, checking weight, moisture content, crispness, chocolate firmness, and flavor profile. One machine even simulates a human bite to measure fracture force and ensure the cookie snaps just right. Then there's the noise. Milano factories are quieter than most cookie plants, with no heavy embossing, no cream-filling pistons, and no high-speed packing arms slamming trays into boxes. The soundscape is mostly conveyor belts humming, air handlers whooshing, and chocolate pumps murmuring in the background. It's more like a pastry kitchen scaled up than a conventional cookie factory. Hygiene standards are bakery grade too. Workers wear full hairnets, gloves, and lab coats. Entry into production zones requires sanitation, foot baths, and air curtains. And because butter is so sensitive to temperature and exposure, rooms are kept cool and clean. Even the flour is filtered and stored under nitrogen pressure to avoid moisture and contamination. Milanos are a study in restraint. There's no glitz, no over-engineering, just exacting control over simple ingredients. From the soft pipe dough to the precise chocolate stripe to the crisp snap of that buttery shell, every step is measured, balanced, and refined to preserve the delicate equilibrium that defines the cookie. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then grated using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, Industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking. And an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable, Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coated, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. Toblerone chocolate production begins with the sourcing and intake of its core raw materials: cocoa mass, cocoa butter, sugar, milk powder, honey, almonds, and soy lecithin as an emulsifier. The distinct taste of Toblerone, known for its smooth Swiss milk chocolate interspersed with chewy nougat and honey almond notes, relies on both the precision of ingredient handling and the consistency of every preparation stage. The factory intake process starts with the arrival of these ingredients at the manufacturing plant's loading bay. Each ingredient is stored and transported under specific conditions tailored to its nature. For example, cocoa mass and cocoa butter, which are highly sensitive to temperature and oxidation, are delivered in thermally stabilized containers that keep them in a semi-solid state. Upon arrival, these containers are immediately transferred into insulated storage tanks inside the facility to prevent exposure to ambient air and humidity. These tanks are purged with inert nitrogen gas to minimize oxidation and preserve flavor integrity. Milk powder, sugar, and lecithin arrive in sealed food-grade sacks or large bulk bins and are lifted by pneumatic suction systems into silo units for temporary storage. Before anything enters the production stream, comprehensive quality assurance testing is conducted. Samples from each delivery are checked for microbiological safety, color, flavor, moisture content, and texture. Specialized equipment such as near-infrared spectrometers and rotary viscometers are used to assess these parameters in real time. Once verified, the production of the chocolate base begins. This base, which will serve as the core medium for all Toblerone bars, is created by combining cocoa mass, cocoa butter, sugar, and milk powder. Each of these components is dispensed into high-capacity stainless steel mixers in precise ratios dictated by the Toblerone formulation. These mixers are automated and fitted with load cells to ensure that each ingredient is weighed to the gram before being introduced to the blend. The contents are mixed at low speed to ensure a homogeneous distribution of particles without excessive aeration. This preliminary mixture, however, is far from the final silky chocolate. At this stage, the texture is coarse and grainy. To refine it, the mix is fed into a 5-roll refiner. The 5-roll refiner is a massive piece of machinery consisting of 5 horizontally aligned steel rollers that compress and shear the chocolate particles down to a size between 18 and 25 microns. This reduction in particle size is critical for mouthfeel. If particles remain larger than 30 microns, the human tongue perceives a gritty texture. Below 20 microns, the chocolate begins to melt smoothly and luxuriously in the mouth. During refining, sensors continuously monitor the gap between rollers and particle fineness using real-time laser diffraction analysis. Excessive refining can result in overheating or fat separation, so the temperature of each roller is actively cooled and monitored to maintain uniform conditions. The refined paste exits the refiner as a silky, thick, and slightly warm material, ready for the next stage, conching. Conching is the step where Toblerone's flavor is truly developed and its texture perfected. The conche machine is a large enclosed vessel that contains mechanical arms or rotors that knead the chocolate mass for several hours. This process serves multiple purposes. First, it evaporates unwanted volatile compounds, such as acetic acid or aldehydes, that may have formed during roasting or refining. Second, it distributes the cocoa butter evenly around each solid particle, coating them thoroughly and improving the overall flow behavior of the chocolate. The conching process typically lasts between 6 and 12 hours, depending on the batch size and the desired profile of the chocolate. During this time, emulsifiers such as soy lecithin are added to reduce the chocolate's viscosity without increasing the fat content. This makes the chocolate easier to mold and coat, while also enhancing its melt-in-the-mouth properties. It is also during conching that the iconic honey and nougat flavor notes of Toblerone begin to be layered in. Honey is added in measured amounts, not just for sweetness, but also to contribute to the product's distinct aroma and chewiness once combined with nougat. The factory conching process uses controlled heat, usually between 45 degrees Celsius and 80 degrees Celsius, to keep the cocoa butter in a liquid state. Temperature control is crucial. Too hot, and the chocolate risks burning or developing off flavors. Too cold, and the process slows, failing to drive off sufficient moisture. Modern conchis are equipped with real-time pH, moisture, and volatile compound sensors that feed back into the control system, allowing operators to adjust mixing speed, arm pressure, or temperature on the fly. Once the conching is complete, the resulting chocolate is an ultra-smooth, shiny, and aromatic mixture. It is pumped into jacketed holding tanks that keep it at a stable temperature of around 30 to 32 degrees Celsius, ideal for downstream processes such as tempering and molding. These tanks are constantly agitated to prevent fat separation and crystallization. The next stage, tempering, is a pivotal process that controls the crystal structure of cocoa butter in the chocolate. Cocoa butter can crystallize in several different forms, but only one form, Form V, produces chocolate that is glossy, firm, and resistant to melting at room temperature. Achieving this form requires carefully heating and cooling the chocolate through a specific temperature curve. Tempering is done in continuous tempering machines where chocolate is first heated to around 45 degrees Celsius to eliminate all previous crystal formations, then cooled down to approximately 27 degrees Celsius to initiate the formation of stable seed crystals. The chocolate is then gently reheated to around 31 to 32 degrees Celsius to eliminate any unstable forms and maintain only the desired crystalline structure. These temperature transitions are tightly controlled by heat exchangers and thermal sensors, which ensure that the flow and crystallization kinetics of the chocolate are kept within narrow limits. With the tempered chocolate now perfectly conditioned and held at its ideal working temperature, it's time to move into one of the most distinctive and meticulously engineered steps of the entire Toblerone production process: molding the chocolate into its iconic triangular bar shape. This is not simply about pouring chocolate into a unique mold. It involves a detailed and highly synchronized series of movements designed to maintain structural integrity, precision alignment, and uniformity across millions of units. The Toblerone mold consists of a series of equidistant triangular cavities arranged in a straight line. Each mold cavity is designed to hold a single triangle of the bar, with narrow necks between them that allow for precise chocolate flow while ensuring each triangle remains individually defined yet conjoined. These molds are made of food-safe, high-strength polycarbonate and are preheated to prevent premature cooling when the liquid chocolate is deposited. Preheating ensures the chocolate flows evenly into every corner of the mold without setting too quickly, which could cause defects like air bubbles or incomplete shapes. Before chocolate enters the mold, the entire cavity array is vibrated at a high frequency using a precision-controlled shaker system. This vibration helps eliminate trapped air, allowing the chocolate to settle smoothly and evenly. The vibrating stage is calibrated to match the viscosity of the chocolate in real time, using inline sensors that monitor the chocolate's flow behavior. Any slight deviation in viscosity can affect how well the chocolate fills the narrow base points of the triangular molds, so the system adjusts shaker speed accordingly. Once the molds are filled, they pass under a leveling scraper to ensure the chocolate surface is perfectly flat along the bottom of the bar, which will ultimately become the base. A second, shorter vibration cycle occurs after this to further consolidate the chocolate and ensure all suspended particles, especially small bits of nougat or almonds, are evenly dispersed within each triangle. If the nougat or honey pieces were to settle unevenly during this stage, it would create inconsistent textures and affect quality. At this point, the filled molds are slowly moved into a multi-zone cooling tunnel. The tunnel is designed to gradually reduce the temperature of the chocolate from around 32 degrees Celsius to below 10 degrees Celsius over the course of several minutes. The zones begin with gentle ambient cooling, progressing through stages of increasingly chilled air, circulated by high-efficiency fans. The slow drop in temperature is crucial. If chocolate is cooled too rapidly, it can develop stress fractures, surface bloom, or uneven crystallization. The cooling system is monitored constantly using digital thermometers, hygrometers, and flow sensors to guarantee uniform airflow and humidity across every inch of the tunnel. As the molded bars pass through each zone, the cocoa butter crystallizes uniformly into the stable Form V lattice structure, locking in glossiness and snap. This stage also causes the chocolate to shrink slightly away from the walls of the mold, which facilitates easy demolding later. Once the bars exit the cooling tunnel, they are still within the molds, but now fully solidified and dimensionally stable. Next, the demolding process begins. The molds are inverted onto conveyor belts, equipped with soft silicone pads that cushion the fall of each bar as it's ejected. Demolding can be done either pneumatically, where jets of compressed air push the back of the mold to dislodge the bar, or mechanically, using plungers that gently press the chocolate out. In either case, sensors monitor the success rate of ejection, and any mold that fails to release the bar is automatically sent to a rework line. Once the Toblerone bars are released from the molds, they are briefly passed through an inspection station where machine vision systems check for mold, fill consistency, breakage, surface defects, and geometric conformity. High-resolution cameras and laser profiling tools compare each bar against stored 3D models. Bars that fall outside tolerance thresholds are marked for reprocessing, where they will be remelted and reintegrated into the production line. The successfully molded and cooled bars now enter the next phase, packaging. Before wrapping, each bar passes through a controlled dehumidification tunnel. This step is critical for preventing condensation during packaging, which could lead to microbial growth, sugar bloom, or spoilage. The dehumidifier maintains an environment below 30% relative humidity and gently warms the air around the chocolate to just above ambient temperature, allowing any moisture on the surface to evaporate without melting the chocolate. Once surface conditions are stabilized, the Toblerone bars move to the wrapping station. Here, the bars are individually picked and aligned onto a high-speed belt, where the characteristic triangular cardboard sleeve is automatically wrapped around each one. The sleeves are die-cut from pre-printed cardboard stock, folded precisely, and glued using food-safe adhesive. Each wrap is barcoded and batch-coded in real time, using inkjet printers synchronized with the production software. After the sleeve is applied, some product variations receive a foil wrapping beneath the cardboard. The foil is cut from gold-colored rolls and folded tightly around the chocolate by robotic arms using pre-programmed pressure patterns that ensure coverage without crushing the delicate points of the triangles. The foil serves as an oxygen and light barrier to prolong shelf life, especially for Toblerone products destined for warmer climates or long export journeys. Every wrapped bar is now scanned and weighed by automated inspection stations. Any unit that falls below or exceeds target weight, accounting for chocolate and packaging, is removed from the line for manual inspection. Those that pass all checks are sorted into bundles depending on product format: single bars, multi-packs, or gift sets. The bars are grouped into cartons by pick-and-place robots. These robots use suction cups and soft grippers to avoid damaging the points of the chocolate triangles. The cartons are then sealed, labeled with lot and traceability data, and stacked into master cases. Each master case is assigned a tracking code and loaded onto pallets using robotic palletizers programmed for maximum cube efficiency and stability. These pallets are then wrapped with stretch film and stored in temperature-controlled warehouses. Warehouse conditions are kept between 16 degrees Celsius and 18 degrees Celsius, with less than 50% humidity to prevent bloom and preserve texture. Pallets are logged into a central warehouse management system that coordinates batch rotation using FIFO principles, ensuring freshness upon delivery. Now that the Toblerone bars have been successfully molded, inspected, and packaged into their iconic triangular sleeves, the next stages of the factory operation transition from chocolate engineering into full-scale logistics, global adaptation, and product diversification, all of which require just as much planning, precision, and technical orchestration as the earlier phases of the chocolate creation itself. The journey from packaged bar to store shelf begins in the factory's outbound logistics area, where every finished pallet is scanned into the warehouse management system. The system integrates with enterprise resource planning software to track inventory levels, prioritize shipping based on destination climate, customs requirements, and expiration dates, and coordinate loading dock activity to maximize efficiency and avoid bottlenecks. At this point, temperature control becomes a dominant concern. Because chocolate is sensitive to thermal shock and prolonged exposure to high humidity or temperatures, all shipments are required to pass through insulated loading bays equipped with temperature buffering systems. These systems maintain consistent conditions even as trucks are loaded, preventing any temporary environmental spikes that might affect product integrity. For shipments destined for nearby distribution centers within a 200-kilometer radius, standard refrigerated trucks are used. These trucks are pre-cooled to the exact storage requirements, typically 16 to 18 degrees Celsius, and each one is fitted with temperature loggers and GPS tracking units that upload data to the central logistics server in real time. Any deviation in internal truck temperature during transit is flagged automatically, prompting quality control checks upon arrival. For export shipments, particularly to regions like Southeast Asia, Africa, or South America, Toblerone products are loaded into refrigerated shipping containers with independent power units, ensuring continuous cold chain conditions during ocean transport that may span up to 3 weeks. Each pallet is labeled with multiple identifiers, including product code, lot number, production time, line number, and temperature certification. These labels are printed using thermal transfer printers that embed RFID chips or scannable QR codes to allow full traceability. This level of detail is critical not only for internal logistics and recall management, but also to meet the regulatory requirements of import authorities in different countries. For instance, Gulf countries may require halal certification to be attached to the consignment, while Japan may demand documentation showing compliance with their unique food additive regulations. Toblerone's global logistics strategy is thus heavily embedded in regulatory compliance, with dedicated teams managing certification, customs documentation, and export logistics. Back within the facility, the production line doesn't operate in isolation. It's part of a broader, synchronized network of production scheduling. Toblerone is not produced as a single SKU, but in a wide variety of formats, each requiring slightly different processing configurations. These include the classic 100-gram bar, 50-gram snack bar, 360-gram gifting box, tiny 12.5-gram miniature pyramids, and specialty editions like white chocolate or dark chocolate variations. Each variation has a specific recipe profile, mold configuration, cooling requirement, and packaging format. Switching between variants requires a carefully managed process known as a changeover. A changeover begins with a complete emptying of all hoppers, pipelines, and depositors currently filled with one chocolate variant. The equipment is flushed using tempered cocoa butter or neutral chocolate mass to clear residual flavors and prevent cross-contamination. Then, the line undergoes a clean-in-place cycle involving detergent wash, water rinse, and final steam sanitization. Sensors measure residual proteins and fats in rinse water to confirm cleanliness. Only after quality control confirms a clean system does the new variant's ingredients enter the production stream. Changeovers also affect the molding system. For example, miniature Toblerone shapes are molded using smaller polycarbonate trays that are swapped in with robotic carriage systems. These molds pass through the same preheating, filling, vibration, and cooling steps as their larger counterparts, but on accelerated cycles due to their reduced volume and mass. The packaging system, too, must adapt. Larger bars require stronger folding cartons with inner trays, while minis are often flow-wrapped and placed into pouches or mixed assortment boxes. To handle this, the line includes modular packaging equipment that can be reprogrammed within minutes using preset SKU profiles. Operators scan a barcode for the new SKU, and all conveyor speeds, arm timing, and print data update automatically. A parallel stream of work takes place in Toblerone's research and development lab, often co-located with the factory or within the company's broader innovation campus. Here, food technologists and process engineers develop new flavor profiles, test alternative sweeteners, and design special edition runs tailored to holidays, partnerships, or regional taste preferences. For example, a limited edition bar infused with salted caramel may require different sugar crystallization controls, or a Ramadan edition might include date extract and modified packaging with Arabic text. Pilot-scale batches are created on miniaturized versions of the factory equipment, allowing experimentation without interrupting commercial-scale output. Every new recipe that graduates from R&D to factory production goes through a phase called scale-up validation. During this stage, the formulation is first made on a semi-commercial line capable of producing thousands of units per hour, and multiple parameters are tested: ingredient behavior under continuous agitation, flow characteristics during tempering, molding fidelity in standard production molds, and thermal stability during cooling. If the results meet the product development benchmarks, full-scale production is approved. Another important dimension of Toblerone's operation is environmental stewardship and factory sustainability. In recent years, the facility has upgraded many of its core systems to reduce carbon footprint, minimize waste, and improve energy efficiency. The chocolate tempering machines now utilize closed-loop thermal exchange systems that recycle cooling energy from one process to another. The air handling systems in the cooling tunnels and clean rooms have been upgraded to variable speed drives and high-efficiency particulate air filtration, significantly cutting energy usage while maintaining product safety. In terms of ingredient sustainability, Toblerone's cocoa is sourced under certified ethical sourcing programs, which ensure that the farms supplying cocoa beans are paid fairly, do not use child labor, and implement agroforestry practices that support biodiversity. These cocoa beans are processed into cocoa mass and cocoa butter by contract processors who follow Toblerone's strict quality and sustainability protocols, including traceability from farm to factory. The almonds and honey, too, are held to exacting standards. Almonds are supplied by certified orchards in California or the Mediterranean, sorted for size and oil content. Honey is sourced with attention to floral origin, ensuring a consistent flavor batch after batch. In-house testing includes pollen analysis, sugar spectrum fingerprinting, and moisture checks. This commitment to sourcing excellence reinforces the brand's identity as a premium Swiss chocolate. Finally, consumer safety and food compliance are at the core of every step of the Toblerone factory. All areas of the facility are subject to strict zoning protocols, separating raw ingredient handling from finished product areas to prevent contamination. Staff undergo regular hygiene training, wear full protective clothing, and enter through sanitation airlocks that include hand washing, boot scrubbing, and compressed air garment cleaning. Equipment is built to hygienic design standards, with no exposed threads, crevices, or moisture traps. Quality assurance checkpoints occur at dozens of locations throughout the line. Metal detectors are installed post-packaging to catch any foreign material. Check weighers ensure that each unit falls within exact mass tolerances. Barcode scanners verify packaging accuracy. And final batch records are signed off by a trained quality technician before any shipment is released. Even the slightest anomaly, an over-tempered batch, a slightly tilted mold, a misaligned wrapper, is caught, logged, and addressed through a root cause analysis process. Every detail matters because Toblerone is not simply a chocolate bar. It's a global symbol of quality, tradition, and precision engineering. What looks like a single, satisfying triangle is actually the result of hundreds of synchronized decisions, operations, and technologies that function in harmony to deliver an unchanging standard of excellence. With the full-scale production, molding, packaging, and international logistics already finely tuned, the final stages of Toblerone's manufacturing process revolve around final distribution, continuous improvement protocols, consumer-facing customization, and digital integration that modernizes how quality and efficiency are sustained across an ever-growing global demand. Once pallets of finished, labeled, and verified Toblerone products are ready for shipment, they enter the outbound logistics management system, where real-time data on shipping routes, order queues, and warehouse availability determine where each batch goes next. The system doesn't just track inventory, it optimizes routes based on transportation cost, shelf life preservation, retail replenishment cycles, and sales forecasts provided by global distribution partners. Whether a shipment is bound for a Swiss airport duty-free zone, a North American grocery chain, or an e-commerce fulfillment center, its path is selected based on minimizing transit time and maintaining perfect storage conditions. Each truck or container that leaves the factory is accompanied by digital and printed documentation that includes compliance declarations, temperature logs, ingredient traceability records, and destination-specific export certificates. These are often required at borders for customs clearance, particularly in markets with strict regulations around food labeling, allergens, or religious dietary requirements like halal or kosher certifications. The factory's compliance team works in sync with shipping personnel, constantly updating their records as international regulations evolve. Inside the production facility itself, continuous improvement is embedded at every level. Daily performance metrics are posted on digital displays throughout the production floor, tracking everything from machine uptime and output per hour to defect rates, waste percentages, and energy usage. Operators have access to touch panel controls that allow them to report faults or initiate adjustments on the fly. When an anomaly is detected, it's logged in a root cause tracking system that prompts follow-up from engineering or quality assurance teams. This immediate feedback loop is designed to prevent small issues from becoming systemic problems. Preventive maintenance also plays a major role in sustaining Toblerone's high production standards. Every piece of equipment in the line, from chocolate mixers to automated packers, is tagged with a maintenance schedule integrated into the plant's CMMS. Operators are prompted automatically when a belt needs replacement, a blade needs sharpening, or a motor requires lubrication. By minimizing unplanned downtime, the factory ensures consistency in output and avoids any deviation from scheduled production volumes. Consumer customization is another frontier in Toblerone's manufacturing strategy. For promotional seasons, corporate gifting campaigns, or regional celebrations, Toblerone offers limited edition bars with printed names, holiday messages, or even national flag motifs. The history of Nerds stretches back to the early 1980s, when they were first introduced to the market as a playful, intensely flavored treat unlike anything else in the candy aisle. The appeal lay in their irregular shapes, their bright colors, and their signature combination of sweet and sour notes. Behind the scenes, however, the magic is created not by whimsy, but by a carefully controlled industrial process. It all begins with the sourcing of raw ingredients. The foundation of Nerds is refined cane or beet sugar, which arrives at the factory in bulk deliveries, often in multi-ton silos or in large paper sacks that are emptied into storage hoppers. This sugar is highly refined to ensure purity, with a moisture content so low that it will not clump during storage or handling. Alongside the sugar come shipments of corn syrup, which acts as a binding and texturing agent, as well as citric acid and malic acid to provide the tartness that defines Nerds' flavor profile. The plant also receives concentrated flavor oils and powdered colors approved for food use. Each batch of these ingredients is tested in a quality control laboratory before it enters the production stream, ensuring compliance with both flavor and safety standards. The production of Nerds begins with a core, which is essentially a tiny granule of sugar that serves as the seed for the candy's build-up process. These seed crystals are often derived from slightly coarser sugar grains that have been screened to a uniform size. The real artistry begins in the heart of the coating pans, large rotating drums that are the beating heart of sugar candy manufacturing. Inside these stainless steel pans, the sugar seed crystals are gently tumbled as a fine mist of sugar syrup is sprayed over them. This syrup is prepared in a heated mixing tank, where granulated sugar is dissolved into water under controlled temperature, often in the range of 110 to 130 degrees Celsius, and then blended with a precise amount of corn syrup to control crystallization. The hot syrup flows through jacketed piping to prevent premature cooling before being atomized into a fine spray within the coating pan. As the syrup coats the tumbling seed crystals, it begins to harden upon contact with the cooler air inside the pan, forming a thin outer layer. Then, a light dusting of dry sugar is sometimes added to further build the surface and maintain separation between individual granules. This cycle repeats dozens or even hundreds of times, each layer adding microns of thickness to the growing candy piece. Operators closely monitor airflow, humidity, and drum rotation speed to ensure that the candies do not stick together or form unwanted lumps. During this stage, the irregular shapes that make Nerds so distinctive begin to emerge. Unlike machine-molded candies that have identical geometry, these sugar-coating pans produce slight variations in size and contour, which means every Nerd has its own unique outline. The gradual layering process continues until the candy reaches the target size, which is typically just a few millimeters in diameter. Once the base size is achieved, flavoring and coloring are introduced. This is a delicate operation, as liquid flavors and colorants must be distributed evenly without dissolving the sugar surface. The pan operator reduces airflow slightly and sprays a concentrated solution of flavor oils, acids, and color onto the candy bed. In many cases, flavors are applied in small incremental sprays with pauses for tumbling in between, allowing the surface to dry and preventing color streaking. The flavors are carefully balanced so that the acids provide tang without overwhelming the sweetness, creating the signature taste that fans recognize instantly. After flavoring and coloring, the candies undergo a polishing step. This involves applying a thin layer of glazing agent, such as carnauba wax, which gives the nerds their characteristic sheen and helps protect them from moisture pickup during storage. The glaze is applied in a separate polishing pan, where candies are tumbled with a small amount of the molten wax until every piece has a uniform shine. At this point, the candies are allowed to cool and set fully, ensuring that their coatings have hardened completely. Cooling may occur in ambient air or in a temperature-controlled chamber that maintains low humidity to prevent stickiness. The fully cooled candies are then transferred via gentle vibratory conveyors to the packaging area. The packaging operation for nerds is an impressive example of precision weighing and high-speed filling. Because the candy pieces are so small and irregular, multi-head weighers are commonly used to ensure accurate portioning. These machines use multiple load cells arranged in a circular pattern, dropping small amounts of candy from each channel until the combined total matches the target weight. This system minimizes giveaway and ensures that each box contains exactly the promised amount. The iconic Nerds boxes are constructed from food-grade cardboard with an inner lining that protects against moisture. The packaging line begins by folding and gluing the flat-printed cartons into their box shape, often with automated carton erectors that can handle hundreds of units per minute. The weighers then deposit the precise quantity of candy into each box through stainless steel chutes. For dual flavor boxes, a partition is inserted inside the carton, and two separate weighing heads feed different candies into each side simultaneously. Once filled, the boxes pass through a closing station, where flaps are folded and glued shut, followed by a coding station that prints lot numbers and best before dates for traceability. The sealed boxes are then collated into larger trays or shrink-wrapped bundles for ease of handling in distribution. Quality control continues all the way through the process. In addition to the raw ingredient checks at the start, samples of candy are pulled from the line at regular intervals to assess flavor consistency, color uniformity, and physical integrity. The hardness of the coating is measured with specialized instruments, and the acidity levels are checked to ensure the sourness remains within the brand's signature profile. Metal detectors are integrated into the conveyor system to ensure no foreign materials make their way into the final product. From the packaging area, the candies move to the warehouse for distribution. Since Nerds are low in moisture and have a hard sugar shell, they are relatively stable during storage. However, they are kept in a cool, dry environment to maintain their texture and prevent color fading. Pallets of finished product are wrapped and staged for shipment to wholesalers, retailers, and export markets around the world. The journey from sugar seed to the vibrant, tangy pellets in your hand is a testament to how much engineering is hidden inside even the simplest candies. Each step, from syrup spraying in massive tumbling pans to the delicate flavor infusion and high-speed filling lines, is executed with precision to deliver the playful, crunchy experience that has kept Nerds popular for decades. Over time, manufacturing technology for Nerds has evolved to improve efficiency and consistency. Early production relied heavily on skilled operators adjusting pans by sight and sound. Today, advanced automation systems track humidity, airflow, and syrup application rates with sensors and feedback loops, ensuring that every batch meets exacting standards. The result is a product that remains faithful to its original flavor and texture while benefiting from modern advancements in food processing equipment. There is also increasing focus on sustainability in candy production. Many factories now recover and reuse heat from syrup cooking kettles, implement water-saving cleaning systems for coating pans, and work with suppliers to source sugar from more sustainable agricultural operations. Packaging too is being reevaluated, with lighter materials and improved recyclability being considered for the future. What makes the production of nerds especially fascinating is the balance between art and science. The process is rooted in classical confectionery techniques that date back centuries, yet it is executed on a scale and with a precision that only modern machinery can achieve. The slight variations in size and shape that give nerds their charm are not flaws, but deliberate results of the panning process, embraced as part of their identity. The story of Twizzlers begins long before the candy reaches the factory floor. As with many mass-produced confections, the foundation is in the sourcing of high-quality raw materials. The primary ingredient is refined wheat flour, which gives Twizzlers their chewy, slightly bread-like texture. This flour arrives at the plant in bulk tanker trucks and is stored in towering silos that protect it from moisture and contaminants. From here, it is gravity-fed or pneumatically conveyed through sealed pipes to the mixing area. Alongside flour, the recipe calls for corn syrup, which provides sweetness, binding power, and flexibility, as well as sugar, which boosts flavor and adds structure. Vegetable oil, often in the form of soybean or palm oil, contributes to the mouthfeel, while food-grade colors and flavorings give Twizzlers their signature appearance and taste. Every ingredient undergoes rigorous inspection in the quality control laboratory before it can be released to production. Flour samples are checked for protein content and moisture levels. Sugar is screened for crystal uniformity, and corn syrup is tested for viscosity and purity. Liquid flavors and colors are reviewed for consistency against reference standards. Once approved, ingredients move into the blending stage, where the transformation from raw material to candy dough begins. The mixing process takes place in large stainless steel horizontal mixers fitted with heavy-duty paddles or spiral blades. The operation starts with a precise ratio of flour and sugar being combined, followed by the gradual addition of corn syrup and water. These mixers operate under controlled speeds to ensure the dough develops evenly without excessive heat buildup. Oil is incorporated next, coating the flour particles and contributing to the dough's smooth, pliable consistency. Throughout mixing, operators monitor temperature and dough texture, making small adjustments to moisture content if necessary. In many plants, this step is partially automated, with sensors tracking torque resistance in the mixer to determine when the dough has reached the ideal elasticity. Once mixed, the candy dough is transferred to the extrusion line. This is the stage where Twizzlers take on their famous twisted rope form. The dough is fed into a large extruder, essentially a high-powered screw press that forces the material through a specially designed die. The screw inside the extruder rotates at a controlled speed, kneading and pushing the dough forward while maintaining an even temperature to prevent premature setting. At the end of the barrel, the die features multiple openings shaped to produce the exact cross-section of a Twizzler rope. For the classic variety, the die includes ridged channels that create the candy's spiral grooves. As the dough emerges from the die, it is still warm and soft, making it easy to shape but vulnerable to deformation. To preserve the precise geometry, the extruded ropes immediately enter a cooling conveyor, a long belt that passes through a tunnel where chilled, dehumidified air circulates. This step lowers the candy's temperature and sets the outer surface while maintaining a chewy interior. The speed of the conveyor is carefully calibrated so that cooling is uniform along the rope's entire length. An interesting detail of Twizzlers' production is that the twist in each rope is not solely a result of the die design. The conveyor belt itself may be equipped with rollers that gently rotate the ropes as they move forward, enhancing the spiral effect. The amount of twist is a delicate balance. Too much rotation can weaken the structure and cause breakage, while too little results in a less distinctive look. After cooling, the ropes are ready to be cut to size. Cutting is performed by high-speed guillotine blades or rotary knives synchronized with the conveyor movement to avoid crushing the candy. For standard snack-sized Twizzlers, lengths are typically between 6 and 8 inches, but the same line can be adjusted to produce miniature bites or extra long versions. The cut pieces now move towards the packaging area, but before they are boxed or bagged, they undergo inspection. Quality control technicians pull samples from the line to check twist uniformity, diameter, weight, and surface texture. The moisture content is measured to ensure the candy retains its chewiness during storage. Flavor is also evaluated by trained sensory panels who compare each batch to established taste profiles. Packaging Twizzlers is a study in efficiency. Depending on the product format, they may be wrapped in flexible plastic film, placed in cardboard trays, or sealed in resealable pouches. The packaging machinery begins with an in-feed system that gently aligns the ropes into uniform stacks. These stacks are then transferred into forming tubes where the plastic film is drawn around them, sealed along the edge with heat, and cut into individual packs. Heat-seal jaws close the ends to lock in freshness and protect the candy from moisture and oxygen. Lot codes, manufacturing dates, and product identifiers are printed directly onto the packaging by inkjet or thermal printers, ensuring traceability for every unit. Sealed packages are collected onto a takeaway conveyor and then collated into larger cartons for shipping. These cartons are stacked on pallets by robotic palletizers, which arrange the boxes in stable patterns and wrap them in stretch film to secure the load. From here, the pallets are moved to the warehouse, a temperature-controlled environment designed to maintain product quality. Although Twizzlers are relatively stable due to their low moisture and high sugar content, excessive heat can cause surface stickiness or deformation, so storage temperatures are carefully regulated. The finished products are then shipped to distribution centers, retail outlets, and export markets. Behind all of this is a network of automation systems and process controls that keep production running smoothly. Modern Twizzlers plants rely on programmable logic controllers to coordinate mixer cycles, extrusion pressures, conveyor speeds, and packaging rates. These systems integrate with quality control data, enabling operators to adjust parameters in real time if a batch shows signs of deviation from the standard. The flavoring of Twizzlers deserves special mention. While the classic strawberry variety is the most famous, the process allows for a wide range of flavors, from cherry to chocolate to licorice. In each case, the flavor oils are blended into the dough at the mixing stage to ensure even distribution. The choice of flavor affects other parameters as well. For example, chocolate varieties may require a slightly different extrusion temperature due to the fat content in cocoa powder, while licorice varieties may use molasses or anise oil that alter dough handling characteristics. Over the years, Twizzlers production has been refined not only for efficiency, but also for consistency. Early methods required more manual handling, with operators guiding ropes off the extruder and cutting them by hand. Today's operations are highly automated, with minimal direct contact between workers and the product. This not only improves hygiene, but also allows for higher output with fewer defects. Sustainability is becoming a greater focus in candy manufacturing as well. Plants are investing in closed-loop water systems for cooling conveyors, energy-efficient ovens for any heat treatment steps, and waste reduction programs that recycle off-spec candy back into the mix when feasible. Packaging materials are also being evaluated for recyclability, with thinner films and plant-based plastics under consideration. What makes the Twizzlers process so fascinating is the combination of bakery-like dough handling with candy-making sweetness. The extrusion technology is similar to that used in pasta production, yet the ingredients and post-extrusion handling are firmly rooted in confectionery science. It is a hybrid process that demands both mechanical precision and an understanding of how sugars, starches, and fats interact under heat and pressure. When you pick up a pack of Twizzlers, you are holding the result of careful ingredient selection, finely tuned mixing and extrusion, precise cooling and twisting, and airtight packaging. Each rope is the product of countless micro adjustments in speed, temperature, and formulation that ensure the candy's texture, flavor, and appearance are exactly as consumers expect. The story of a Haribo gummy begins with the ingredients, each of which is selected for quality and consistency. At the heart of the recipe is gelatin, a protein derived from collagen that gives the candy its characteristic elastic texture. This gelatin arrives at the factory in dry, granulated form and must be carefully hydrated before use. Alongside gelatin, the formulation includes glucose syrup, often produced from wheat or cornstarch, which provides body, prevents crystallization, and contributes to the chewiness. Sugar is another mainstay, giving sweetness and structural integrity. Additional ingredients include citric acid for tartness, natural and artificial flavorings for each variety, and food-safe colorants to create the rainbow of hues that define Haribo's product line. Every batch of ingredients undergoes rigorous testing in a quality control laboratory before it reaches the main production floor. Gelatin is checked for bloom strength, which determines the firmness of the finished candy. Glucose syrup is tested for solids content and viscosity, ensuring it will flow and set properly in the cooking process. Flavor and color concentrates are measured for potency and compared against established standards. Only when the raw materials pass inspection are they released to the production team. The first major step in making Haribo gummies is the cooking process. This begins in large stainless steel vessels called dissolvers or cooking kettles. Here, sugar, glucose syrup, and water are combined and heated under controlled conditions. The heating process brings the mixture to a high temperature, often in the range of 110 to 140 degrees Celsius, allowing the sugars to dissolve completely and the syrup to thicken. Once the sugar syrup reaches the correct density, pre-soaked gelatin is added. The gelatin is never boiled, as high temperatures would damage its gelling properties. Instead, it is stirred in gently once the syrup has cooled to a safe range, typically between 80 and 90 degrees Celsius. At this point, flavorings, acids, and colors are added. For gummy bears, this might include lemon, orange, raspberry, apple, and strawberry flavor profiles, each paired with a corresponding color. The additives are metered in with precision pumps to ensure every batch is consistent in both taste and appearance. Stirring must be thorough but gentle to avoid incorporating excess air bubbles, which could mar the candy's surface. Once the mixture is fully blended, it is ready to be formed into shapes. This is where Haribo's distinctive starch molding process comes into play. The company uses a method called the Mogul system, an automated production line that allows liquid candy to be deposited into detailed molds with incredible precision. The process begins with large trays filled with a fine, dry cornstarch powder. This starch serves two purposes. It prevents the sticky candy from clinging to the trays, and it helps wick away excess moisture during the setting stage. Each tray passes through a stamping unit where metal dies press the shape of the candy into the starch. Tiny, bare outlines, cola bottle profiles, or whatever form is being produced. The impressions are crisp and exact, ready to receive the warm, liquid mixture. From the cooking kettles, the candy syrup is pumped through heated pipelines to a series of depositor nozzles. These nozzles align perfectly with the starch impressions and release measured amounts of syrup into each cavity. The depositor can switch flavors and colors quickly, allowing for multiple varieties to be produced on the same line with minimal downtime. Once deposited, the trays of liquid candy are conveyed into a long climate-controlled curing room. Here, they rest for 12 to 72 hours, depending on the recipe, temperature, and humidity. During this time, the gelatin network fully sets, giving the candy its final chewy texture, while the starch continues to absorb surface moisture. The curing rooms are kept at specific humidity levels to prevent the candies from drying out too much or becoming sticky. When curing is complete, the trays move to the demolding stage. The gummy shapes are gently lifted from the starch, which is recovered, dried, and sieved for reuse in future molding. Any excess starch clinging to the candies is removed through a combination of mechanical shaking and soft air jets. The gummies, now fully formed, have a matte appearance and a slightly tacky feel at this stage. To give them the glossy finish consumers recognize, the candies are transferred to large rotating drums called glazing pans. Inside, they are tumbled with a thin coating of food-grade waxes such as carnauba or beeswax, along with oils that enhance shine and prevent sticking. The glazing process is quick but crucial, as it also provides a protective barrier against moisture changes during storage. With their appearance perfected, the gummies proceed to the packaging area. Here, high-speed conveyors feed them into multi-head weighers, machines equipped with multiple hoppers that dispense exact amounts to achieve the target package weight. The candies are dropped into pre-formed bags or into the forming tubes of vertical form-fill-seal machines. These machines create a bag from a continuous roll of printed film. Seal the bottom, fill it with the candy, then seal the top in one continuous motion. For variety packs, sophisticated sorting systems group different gummy shapes and flavors in precise ratios before they reach the weighing step. This ensures that every bag contains the intended assortment. Packaging films are chosen for their barrier properties, keeping the gummies fresh while displaying bright branding. Each bag receives a lot code and best before date for traceability, then passes through metal detection equipment as a final safety measure. The finished bags are gathered into cartons, stacked onto pallets, and wrapped in stretch film to stabilize them for shipping. Pallets are moved to temperature-controlled storage areas until they are loaded onto trucks bound for distribution centers and retailers around the world. Throughout the entire process, quality control remains a constant presence. Samples from each batch are taken at multiple points, from syrup cooking to molding, curing, and packaging, to ensure that every aspect meets Haribo's specifications. Technicians test texture with penetrometers to confirm the perfect chew, measure pH to monitor acidity, and use colorimeters to verify hue accuracy. Flavor panels taste test samples to ensure the product matches established sensory profiles. The production of Haribo gummies has evolved significantly over the decades. Early batches were made by hand in small copper kettles and poured into starch molds one tray at a time. Today's lines can produce hundreds of thousands of pieces per hour, with computerized systems controlling every variable. Yet the core principles remain the same: quality ingredients, precise cooking, careful molding, and patient curing. There is also a growing emphasis on sustainability within Haribo's operations. Many plants now use energy recovery systems to capture heat from cooking processes, recycle starch indefinitely, and source gelatin and sugar from more sustainable supply chains. Efforts to reduce packaging weight and increase recyclability are also underway, ensuring that the joy of gummy bears has a smaller environmental footprint. What makes Haribo's process fascinating is the blend of old-world confectionery craftsmanship and high-tech automation. The mogul molding system, for instance, is an industry standard, yet it still relies on principles that candy makers have used for over a century. The long curing time is a reminder that some aspects of candy making simply cannot be rushed if the desired texture is to be achieved. By the time a bag of Haribo gummies reaches the shelf, it has undergone a transformation from raw sugar, syrup, and gelatin into a perfectly shaped, flavorful, and brightly colored treat. Behind each piece is a network of ingredient sourcing, controlled cooking, precision molding, and patient curing, all supported by layers of quality control and packaging expertise. It all begins with the raw materials. For Kellogg's cornflakes, the primary ingredient is whole grain yellow corn, chosen for its high starch content, consistent kernel size, and clean flavor profile. The corn is sourced from farms that meet strict quality standards, often grown in regions where soil conditions, temperature, and moisture levels yield the optimal crop. The grain suppliers must pass multiple certification checks to ensure there are no contaminants, pesticides above allowed thresholds, or off-spec kernels. Alongside the corn, other ingredients such as sugar, malt flavoring, and a precise blend of vitamins and minerals are procured from certified ingredient suppliers. Even minor ingredients undergo laboratory testing for purity and safety before they are ever allowed into the production flow. When the corn arrives at the Kellogg's plant, it is unloaded from bulk transport trucks or rail cars into massive silos. These silos are fitted with aeration systems to keep the grain dry and prevent mold growth. Before storage, the corn passes through a preliminary cleaning system. This includes vibrating screens to remove large debris, aspirators that blow away dust and light particles, and magnetic separators to capture any stray metallic fragments. The cleaned corn is then weighed using automated bulk scales, ensuring precise tracking of raw material usage for both production planning and regulatory compliance. From storage, the corn moves toward the first processing step, cooking. But before cooking, the kernels need conditioning. This involves sending them through a pre-wet process in which they are steamed lightly or soaked in warm water to raise their internal moisture content to the right level for even cooking. Moisture meters along the line continuously monitor this process. Once conditioned, the kernels are conveyed to large pressure cookers, sometimes referred to as steam cookers or rotary pressure vessels. These massive stainless steel cylinders rotate slowly while injecting steam and adding a carefully measured solution of sugar, malt flavor, and salt. The steam not only cooks the kernels, but also helps the added flavors penetrate evenly into each piece of corn. The cooking process gelatinizes the starch inside the kernels, making them ready for the next transformation. After cooking, the hot, softened kernels need to be cooled and partially dried. They exit the cooker onto a series of vibrating cooling conveyors where ambient or slightly chilled air is blown across them. This stops the cooking process, stabilizes the texture, and prepares them for the critical flaking stage. However, the corn is still too moist to be flaked properly. It first enters large industrial dryers, often drum style or fluidized bed dryers, which reduce the moisture content to an exact level that will allow the flakes to shatter cleanly, rather than smear or tear during rolling. The drying process is closely monitored by moisture probes and computer-controlled exhaust systems to maintain uniformity. The next stop is tempering. Tempering involves holding the cooked, dried kernels in large bins for several hours so the remaining moisture distributes evenly throughout each kernel. This equalization is key to creating flakes that cook evenly in the final toasting step. The bins are equipped with gentle agitators or slow conveyors to prevent clumping and to keep airflow steady. Once tempered, the kernels are ready for the flaking process. Here, they pass through massive flaking mills. Each mill consists of two large, precision-ground steel rollers, often cooled internally to prevent heat buildup. These rollers press each kernel flat in a single pass, creating the familiar, thin, oval shape. The gap between rollers is set to a fraction of a millimeter and is adjusted automatically to ensure all flakes have the same thickness. The flaking mill is one of the most critical pieces of equipment because the thickness of the flake determines not only the texture, but also the way it will toast and absorb milk later on. Freshly flaked corn is still pale and slightly soft, so it moves immediately into the toasting ovens. These ovens are long, multi-zone conveyors where hot air, often at temperatures over 300 degrees Fahrenheit, flows over and through the flakes. The first zones drive off remaining moisture, while the later zones caramelize the sugars and develop the golden brown color. The toasting stage is where the signature crunch develops as the starch matrix hardens. The aroma at this point is unmistakable. Warm, slightly sweet, and distinctly cereal-like. Automated sensors monitor the color and moisture level, and adjustments to air temperature or conveyor speed can be made in real time to maintain consistency. Once toasted, the flakes are cooled on open conveyor belts with filtered ambient air. Rapid cooling helps lock in crispness and prevents condensation inside the packaging later. At this stage, the cereal may pass under a vitamin and mineral application system. In some Kellogg cereals, a fine mist or powder of fortified nutrients is sprayed or dusted onto the flakes, then gently tumbled to ensure uniform coating. The application rate is measured to fractions of a gram to comply with nutritional labeling requirements. From here, the flakes head toward the packaging. Before they can be boxed, the cereal is screened to remove overly small particles or broken flakes. These screenings may be collected for use in other products or as livestock feed. The main product stream passes through a final quality check, which can include metal detectors, optical sorters, and even X-ray scanners to detect any foreign matter. Samples are pulled at regular intervals and sent to an on-site lab, where technicians test for moisture content, color, flavor, and texture to ensure the batch meets Kellogg's specifications. The packaging line is a marvel of precision. The cooled cereal is metered into form-fill seal machines or pre-made bag fillers. In the classic box format, an inner bag made of food-grade plastic film is formed from a continuous roll filled with an exact weight of cereal using high-speed scales, then heat-sealed. The filled bag is automatically inserted into a printed cardboard carton, which is glued shut and stamped with a production code for traceability. Packaging machines operate in perfect synchronization with the upstream production flow to prevent overfill, underfill, or product jams. Sealed boxes travel down conveyors to be bundled into shipping cases. Robotic case packers arrange multiple boxes into corrugated cardboard cases, which are sealed and labeled with both barcodes and batch codes. These cases are stacked by robotic palletizers into tall, stable loads, often wrapped with stretch film to secure them for transport. From the moment the corn arrived at the plant, the environment has been strictly controlled for food safety. Air is filtered, surfaces are sanitized regularly, and all equipment is cleaned in place using automated cleaning systems that circulate hot water and food-safe detergents through the machinery. Employees follow stringent hygiene protocols, including wearing protective clothing, hairnets, and gloves. Every step in the process is documented for traceability, so that in the rare event of an issue, the source can be identified and contained quickly. Once the pallets of finished cereal leave the plant, they are loaded into clean, dry trucks or shipping containers. Distribution centers receive the pallets, store them under controlled conditions to prevent moisture pickup or crushing, and coordinate shipments to retailers. Retail stock rotation ensures that consumers always get cereal at peak freshness. The shelf life of cornflakes is typically several months when stored in a cool, dry place, thanks to the low moisture content and protective packaging. Beyond the basic process, Kellogg's has invested in continuous improvement and technological innovation in its plants. Automation now allows for real-time monitoring of every parameter, from the temperature inside the toasting oven to the precise thickness of flakes coming off the mill. Data analytics can flag trends before they become defects, enabling preventive adjustments. Energy efficiency measures such as heat recovery from ovens and optimized air handling systems have been integrated into many plants to reduce environmental impact. Cheerios production begins long before the famous little toasted oat rings take shape on the factory line. It starts with selecting the right oats because in a product like Cheerios, where oats are the star ingredient, the raw material defines the flavor, texture, and nutritional profile. The oats are sourced from farms that grow specific varieties of whole grain oats prized for their uniform kernel size, high beta-glucan content, and consistent milling performance. These farms are often located in cooler climates where oats thrive, and the crops are harvested, cleaned, and transported in bulk to the manufacturing plant under strict quality control conditions. When oats arrive at the facility, they are unloaded into massive storage silos equipped with aeration systems to maintain dryness and prevent spoilage. Before being accepted into the main storage bins, the oats pass through mechanical cleaning systems. These systems remove dust, small stones, and plant debris using vibrating screens, air aspiration units, and magnetic separators that capture any trace of metal contamination. Every incoming lot of oats is also tested in the plant's quality control lab for moisture content, protein level, microbial safety, and the absence of unwanted residues. The next step is oat milling. In the Cheerios process, oats must be transformed from raw groats into a workable form for extrusion. This begins with dehulling, which removes the outer husk from each oat kernel. The cleaned oats are fed into impactor hullers, where centrifugal force cracks the hulls without damaging the inner groats. The hulls are separated from the groats using aspiration and gravity tables, and the groats proceed to a kiln for heat stabilization. Heat stabilization is a controlled toasting step in which the groats are gently heated to deactivate enzymes that can cause rancidity. This step also enhances the nutty flavor of the oats. From there, the groats are rolled or ground into oat flour. For Cheerios, a blend of whole oat flour and sometimes additional grain flours like cornstarch or wheat starch is used to create the right dough properties for extrusion. The oat flour is measured precisely, and minor ingredients such as sugar, salt, and a vitamin-mineral premix are prepared in separate dosing hoppers. All these dry ingredients are fed into a pre-mixing system, where they are blended into a uniform mix before moving to the wet mixing stage. Wet mixing takes place in an industrial preconditioner or mixer, where water and sometimes steam are added to the dry mix. This creates a damp, pliable dough. The ratio of water to dry mix is carefully controlled because it determines how the dough will behave in the extruder. Sensors inside the mixer continuously measure dough temperature, moisture, and homogeneity. This hydrated dough is conveyed immediately into the heart of the Cheerios process, the extrusion system. Cheerios are made using a rotary die extruder. The dough is fed into the extruder barrel, where rotating screws knead and compress it under controlled heat and pressure. The barrel is divided into zones, each with a specific temperature and mechanical shear setting. As the dough moves forward, the heat and pressure partially cook the starches and gelatinize them, creating a texture that will puff slightly when released from the die. At the end of the barrel, the dough is forced through a die plate that has hundreds of tiny, ring-shaped openings. Each opening has a small pin in the center, creating the hole of the Cheerio as the dough extrudes around it. As the dough emerges from the die, it is cut to size by high-speed rotating knives mounted just outside the plate. The freshly cut rings are soft, warm, and slightly expanded. These rings now enter the drying and toasting stages. First comes the primary drying conveyor, where warm air is blown over the pieces to reduce moisture and prevent sticking. After this initial drying, the Cheerios are transferred to large, continuous toasting ovens. These ovens operate with multiple temperature zones. In the early zones, moisture is driven off steadily, and in the later zones, higher heat creates the light brown toasted color and enhances the flavor through Maillard reactions. The toasting step is critical for the signature crunch of Cheerios. Moisture sensors and color cameras monitor the product as it travels through the oven, and computer-controlled adjustments are made on the fly to keep the output consistent. After toasting, the Cheerios must be cooled before packaging. They move along cooling conveyors where filtered ambient air is circulated. The goal is to bring the product to a stable temperature, so condensation will not form inside the packaging. This also allows the texture to set fully. In some varieties, a light coating of sugar syrup or flavoring may be applied at this stage using a rotating drum or tumbler. But for classic plain Cheerios, no additional coating is added after toasting. Next, the cooled cereal is sifted to remove small fragments or broken rings, which are collected for use in other applications or for animal feed. The main product stream passes through a final quality control system that includes metal detection, weight checks, and sometimes optical sorting to ensure that every piece is intact and meets size specifications. Samples are pulled for sensory evaluation, which includes tasting for flavor, checking crunch, and verifying that the shape and color meet the brand standard. Packaging begins with precise weighing. Multi-head weighers dispense exact amounts of cereal into form-fill-seal bagging machines. In the classic box format, an inner bag is formed from a roll of plastic film, sealed at one end, filled with cereal, and then heat sealed at the top. Automated arms place the sealed bags into pre-printed cardboard cartons. Each carton is glued shut and stamped with a lot code that contains information about the date, time, and line of production for traceability. These cartons travel along conveyors to case packers, where machines arrange them into corrugated shipping cases. The cases are sealed, labeled, and then stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability during shipping. Finished pallets are stored temporarily in a distribution warehouse with temperature and humidity controls to preserve product freshness. From the distribution center, the pallets are loaded into clean, dry transport trucks and shipped to retailers nationwide. Retail stock rotation ensures that older product is sold first, keeping Cheerios at their optimal freshness for consumers. The shelf life of Cheerios is generally several months due to their low moisture content and protective packaging, but quality is highest in the weeks immediately after production. Throughout the entire process, food safety and quality assurance are paramount. The factory environment is designed for easy cleaning and sanitization with enclosed systems that protect the product from airborne contamination. Employees follow strict hygiene protocols, including wearing hairnets, gloves, and uniforms, and undergoing regular training in food safety practices. Many parts of the plant operate under hazard analysis and critical control points plans, ensuring that every stage, from raw grain to finished package, is monitored for safety risks. Cheerios production is also heavily automated, with control systems tracking hundreds of variables in real time. Data on dough moisture, extrusion pressure, oven temperatures, and packaging line speeds is logged continuously. This allows operators to detect subtle deviations and correct them before they impact the final product. Over the years, the efficiency and precision of Cheerios manufacturing have improved dramatically through advances in automation, ingredient handling systems, and real-time quality monitoring. The making of Frosted Flakes begins with one key ingredient: corn, but not just any corn will do. The factories that produce Frosted Flakes work with carefully selected varieties of yellow dent corn that have the right starch composition, kernel size, and moisture profile to create large, uniform flakes with a crisp bite. These corn varieties are grown in regions where climate and soil conditions produce consistent, high-quality harvests. Before a single load of corn is accepted, it must pass rigorous inspections for moisture content, kernel integrity, absence of mold or mycotoxins, and overall cleanliness. This ensures that, from the very start, the product's signature taste and texture are protected. The corn arrives at the plant in bulk trucks or rail cars and is unloaded into massive storage silos. These silos are fitted with aeration systems that keep the grain cool and dry to prevent spoilage. Before the corn can be stored, it is cleaned using a series of mechanical processes. Vibrating screens remove large debris, aspirators blow away dust and lightweight particles, and magnets capture any stray bits of metal that may have entered during harvesting or transport. After cleaning, the corn is weighed using bulk scales, allowing the plant to track exactly how much raw material will be processed into frosted flakes. Once the corn is ready for production, it is first conditioned. Conditioning involves soaking or steaming the kernels to bring their internal moisture to an optimal level for cooking. This step softens the kernels and helps them absorb flavors more evenly later in the process. The conditioned corn is then fed into massive rotary pressure cookers. In these cookers, the kernels are tumbled slowly while being injected with live steam under pressure. A syrup blend of sugar, malt flavor, and a pinch of salt is added, infusing the corn with a sweet, malty taste that will deepen during toasting. This cooking stage gelatinizes the starch inside the kernels, transforming them from hard grain into a tender, flavor-packed base. When the cooking cycle is complete, the hot softened corn is discharged onto cooling conveyors where fans blow ambient or slightly cooled air over the kernels. This halts the cooking process and stabilizes their texture. At this point, the kernels still contain too much moisture to be flaked properly. They move into large industrial dryers, either drum-style or fluidized bed designs, that gradually remove water until the kernels reach the precise moisture level needed for flaking. The drying process is tightly controlled because too much drying will cause the flakes to crumble, while too little will cause them to smear or tear during rolling. After drying, the corn undergoes tempering. This step involves holding the kernels in large bins for several hours to allow the remaining moisture to distribute evenly throughout each kernel. Tempering ensures uniform flaking and helps prevent uneven toasting later. Gentle agitators or slow-moving conveyors in the bins keep the kernels from clumping together while promoting even airflow. Now comes one of the most important steps in the frosted flakes process: flaking. The tempered kernels are fed into massive flaking mills where pairs of enormous, precision-ground steel rollers press each kernel flat in a single pass. The rollers are often water-cooled internally to prevent heat buildup, which could cause sticking or premature cooking. The gap between rollers is adjusted with extreme precision to produce flakes of consistent thickness. This thickness is critical. It determines how the flakes will toast, how they will break in the mouth, and how long they will stay crisp in milk. Freshly flaked corn is pale, soft, and flexible, so it immediately enters long toasting ovens. These are continuous conveyor ovens with multiple heating zones. In the early zones, hot air drives off remaining moisture, locking in the flakes' shape. In the later zones, higher heat brings out the golden brown color, deepens the flavor, and crisps the texture. The toasting stage is also when much of the sweet, roasted aroma is developed. Sensors throughout the oven monitor moisture levels and color, and adjustments to temperature and conveyor speed can be made instantly to keep every batch consistent. Once the flakes are perfectly toasted, they are cooled on open-air conveyor belts to stabilize their structure. This cooling step also prepares them for the next stage that gives frosted flakes their name: sugar coating. The cooled flakes enter large, rotating tumblers known as coating drums. Here, a warm sugar syrup is sprayed onto the flakes in a fine mist. The syrup is made from refined sugar dissolved in water and heated to the right viscosity so it coats evenly without soaking the flakes. As the flakes tumble, every surface becomes covered in a thin, glossy layer. The amount of syrup applied is carefully measured to achieve the brand's signature sweetness without overpowering the cereal's natural corn flavor. After coating, the flakes pass through another drying system, often a warm air tunnel, which removes excess moisture from the syrup and crystallizes the sugar onto the flakes' surfaces. This creates the sparkling, crunchy coating that stays intact until the cereal is submerged in milk. The drying time and temperature are crucial. Too short and the sugar will be sticky. Too long and it may over-caramelize. Following coating and drying, the cereal undergoes final quality checks. It is sifted to remove broken flakes and small sugar granules. The main product stream passes through metal detectors and sometimes X-ray scanners to ensure there are no foreign materials. Samples are pulled regularly for moisture testing, color analysis, sweetness measurement, and texture evaluation. Taste panels may also evaluate random samples to confirm flavor consistency. The finished frosted flakes are then ready for packaging. The cooled flakes are conveyed to multi-head weighing machines that dispense exact portions into high-speed packaging lines. For the classic box format, an inner bag is formed from a continuous roll of food-grade plastic film, sealed at the bottom, filled with cereal, and then heat-sealed at the top. The sealed bag is automatically inserted into a pre-printed cardboard carton. The carton is glued shut, stamped with a production code for traceability, and checked by sensors to ensure it is properly sealed. From here, the cartons are conveyed to case packing machines, where they are grouped into corrugated shipping cases. These cases are sealed with adhesive tape or hot glue, labeled with batch information, and stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability during transit and stored in a climate-controlled warehouse until they are shipped. Every step of the frosted flakes process takes place in a facility designed with strict food safety controls. Air handling systems keep dust and contaminants out of production zones, while stainless steel surfaces are regularly cleaned and sanitized. Automated clean-in-place systems wash the interior of cookers, dryers, and coating drums without dismantling the equipment. Workers wear protective clothing, hairnets, and gloves, and they follow hygiene protocols to prevent contamination. Once the product leaves the factory, it travels to distribution centers, then to retailers. Stock rotation at the store level ensures that consumers get fresh product with the sugar coating intact and the flakes as crisp as they were on the day they were made. Proper storage, cool, dry, and away from direct sunlight, keeps frosted flakes in peak condition for months. Behind every box of frosted flakes is a tightly controlled sequence of thermal, mechanical, and chemical transformations. From the high-pressure steam cooking that gelatinizes the starch, to the precise flaking that creates the perfect surface for sugar adhesion, to the final toasting that seals in crunch and flavor, every step is engineered for consistency. This is why a bowl of frosted flakes tastes the same, whether it was made in Michigan, Canada, or halfway across the world. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated. Five Guys moves thousands of pounds of beef and buns through a supply chain so intense it runs like a high-speed burger machine. Behind every fresh, made-to-order meal is a massive factory system designed to deliver consistent flavor with zero shortcuts. In this documentary, we go inside the operation powering one of America's most iconic burger chains, from raw ingredients to grill-ready perfection. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean-to-fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated, but the buns are loaded in temperature-controlled staging areas and packed in sealed corrugated boxes to maintain freshness during transit. Any deviation in delivery, timing, or packaging temperature triggers a rejection at the restaurant level. In store, the buns are stored at room temperature in designated bread racks, often rotated using FIFO principles. Staff members are trained to inspect buns visually and by touch. Any signs of excess firmness, moisture, or spotting lead to immediate disposal. Each bun is hand-prepared on-site, toasted on a grill with a light coating of melted butter before it becomes the vehicle for the burger build. This final touch, though simple, is only possible because of the structural integrity and texture delivered by the bakery's industrial process. Now that the core components of a Five Guys burger are accounted for, the beef, the fries, and the buns, it's time to examine the supporting elements that complete the burger experience: bacon, cheese, toppings, and condiments. These items may seem simple, but each is chosen and prepared with deliberate intent and, in most cases, centralized at an industrial level before being delivered to restaurants. Starting with bacon, Five Guys sources thick-cut, naturally smoked strips from approved pork processors in the US. The bacon is not fully cooked at the factory. Instead, it's partially cooked or pre-rendered to about 60 to 70% doneness, then chilled and vacuum packed in clear plastic pouches. These pouches are labeled and sorted by weight and count per case, with each case tagged for traceability. The bacon is cooked to completion in the restaurant, where staff lay it flat on the grill and crisp it to order. This two-step process, initial industrial cooking followed by final preparation, ensures food safety, flavor development, and grease reduction